All right, you guys, so new chapter, last chapter of chapter 5, and we're going to learn our last round of identities. They're called the half-angle identities. In practice, these are extremely hard to use. I actually think the homework is kind of limited, because these are very tough to use. But I think obviously there's something we need to learn, there's something we need to do and go through, and so we're going to go ahead and we're going to do it. So here's basically what they are. We have the sine of a half angle is equal to this crazy thing. Cosine of a half angle is equal to this crazy thing. And then we actually have 3 different versions of the tangent of a half angle. And so that's pretty crazy. Again, just like the double angle for cosine, which one of those 3 I use depends on the situation, and we get a lot of different answers. Another thing that you will note, unlike the double angle formulas that we had earlier when we were using those, let me pull those out, right? Even though they're, here's our double angle from a previous video, there's no plus or minuses anywhere. So these this tells us that these are very strong inequalities. They work just about in any circumstance that we have. But in the half angle formulas, you'll notice that there's a plus minus for the sine, for the cosine, and one of the tangents. So these are very what's the word? I don't want to use the word weak, but they're very you got to worry about which quadrant we're in, basically. So which quadrant is A over 2 in, and that helps us basically determine what our plus minus. Do we consider the plus route or the minus route? So they're very sensitive. There's the word I'm looking for. I don't even know if I pronounced it right, but they're very sensitive to the quadrant that we're in. And you notice for the double angle formulas, we didn't really worry about that, right? I mean, we did and we didn't, but it was more for if we were trying to find the sine of A or the cosine of A or the tangent of A when we worried about that. We didn't really worry about it too much for the double angle. So that makes this set very strong and why they're probably used more than these guys, but they're used nonetheless. And what I like to do is walk you through, I think the book has a proof, there's all kinds of proofs online, but let me walk you through a proof because it's very famous for a trick that's often done in mathematics to make somewhat of a substitution to get what I want. All right, and so here's what this is. So let me prove the sine for you guys, and then the cosine will be similar, and then pretty much once we have those two, we have tangent, right? Because tangent is sine over cosine. So it's imperative that we prove these two, and once I prove one, you kind of have the idea for the second. So here's what we know. Using our double angle formulas, we actually know that the cosine of 2 theta, let me go ahead and use theta, is equal to 1 minus 2 sine squared theta, right? So that is from our double angle formula where I replace the A with theta. And then here's the trick we're going to do. We're going to actually let theta equal A over 2. So I'm going to make a substitution. Very, very famous math trick to try to get what the result that I want. So if I make the substitution, this now becomes the cosine of 2 times A over 2 minus 1 minus 2 sine squared of A over 2. And you can see this trick pretty much helped us out because I'm essentially trying to find what is the sine of A over 2. And what I have is I have an expression with the sine of A over 2 in it. We just need to solve for it. So let's get to work. Let's get cracking. That's an equal sign, by the way. So when I take A over 2 and multiply it by 2, on this side I get the cosine of A equals 1 minus 2 sine squared of A over 2. If I subtract 1 from both sides, we basically get the cosine of A minus 1 is negative 2 sine squared of A over 2. And then if at this stage I divide both sides by negative 2, what we essentially have, let me kind of rewrite some stuff around. This is sine squared of A over 2. That negative down there, if I apply it to the top, I get 1 minus the cosine of A all over 2. And then you can pretty much see we're done, because if I take the square root of both sides, number one, I've introduced a plus minus, and we have that the sine of the half angle is plus or minus the square root of 1 minus the cosine of A all over 2. And so there's basically the proof for that one. And of course you can imagine for this one, what we're going to do is we're going to use the same double angle formula, but this time it'll be the cosine version. Right? So that's another way to write the cosine of the double angle. Again, letting theta equal a over 2. This becomes the cosine of 2 times a over 2 equals 2 cosine squared of a over 2 minus 1. And so we're basically now just using our algebra to solve for cosine of a over 2. So add 1 to both sides. By the way, the 2's cancel out here, so we have 1 plus the cosine of a equals 2 cosine squared a over 2. And then if we divide by 2, we have the cosine squared of a over 2 is 1 plus the cosine of a over 2. And of course, if we take a square root now, introduce a plus minus, we have what we're looking for. So the cosine of a half angle is plus or minus the square root of 1 plus the cosine of a all over 2. So we basically have proven the sine and the cosine. And so basically the tangent now becomes pretty easy, because what do we know about tangent? Let me go ahead and put this on another piece of paper. Right? So what do we know about tangent? Well, it doesn't really matter what the angle is, right? Tangent of a over 2 would be the sine of a over 2 divided by the cosine of a over 2. And so using what we have here, this is plus or minus the square root of 1 minus the cosine of a over 2 divided by plus or minus the square root of 1 plus the cosine of a over 2. Alright, so we have a plus minus, so our final answer will definitely have a plus minus in it. And then when I have a radical of the upstairs and the downstairs, it's the same thing as taking the radical of the whole thing. If I take a fraction and divide it by a fraction, we're effectively multiplying by a reciprocal. The 2's divide out, and there is one of the versions for the tangent. So tangent of a half angle is plus or minus the square root of 1 minus cosine of a and 1 plus the cosine of a. So how do we get the other 2? Well, the way we get those is we rationalize one of our denominators. So let's go ahead. I think let's begin. Let me just work on this on the bottom. So we got 1 minus cosine of a, 1 plus the cosine of a. So if I multiply both top and bottom by 1 minus the cosine of a, right, what we get down below is 1 minus cosine squared of a. And upstairs, what we eventually get, if we FOIL that out, we get a 1 minus 2 cosine of a plus cosine squared of a. Right? So we get a negative cosine, negative times a negative is a positive. Alright, so there's what we have there. The bottom, we know that to be sine squared of a, right, using our Pythagorean identity. And then upstairs, what we basically have, right, for what we have upstairs is we basically, how about I just rewrite it in factored form, because that's actually what I want to get. We have 1 minus the cosine of a squared, right? So let me refactor that out. And the reason I wanted to do that, I lost track, is remember what we want to do here is we want to basically, that was what's inside the radical there. So we're basically talking about the square root of 1 minus cosine of a squared all over the sine of a squared. And if I square everything, what we get is 1 minus cosine of a all over the sine of a. And since I'm squaring everything, right, that's pretty much why the plus minus goes away, because it doesn't really matter if I'm plus or minus. When I square stuff, like I'm doing right here, right, everything is positive no matter what. So that basically proves that one. All right, and of course, how do I get that third one? Well, we'll start by taking that guy, and we'll actually multiply both in top bottom by 1 plus cosine of A. So upstairs we get 1 minus cosine squared A. Downstairs we get 1 plus cosine of A squared. And then pretty much the rest is history. We got sine squared A all over 1 plus cosine A squared. So I'm squaring everything, so it doesn't really matter plus or minus, right? When I take that square root of all that, because remember we're just playing around with what's inside, we get sine of A 1 plus cosine of A, right? I think I lost the edge of that sheet there. All right, and so that basically proves the third one. All right, so there's your proofs using a famous substitution trick, and then just using our definition for tangent, and then basically to get the other two, we're playing around with rationalizing a denominator by multiplying either the top or bottom by a conjugate, getting us the other two. So there's your proof. Now what we got to go do is use them. Find exact values, rewrite expressions, prove identities. And you'll see those in videos coming soon.